Hello, everybody. This is for the course Maths2099, Linear Algebra in the University of New South Wales. In this problem, I am going to solve two problems, question 68 and 70, about how determinants will be affected with respect to the column operations or row operations. In this question, we would like to solve all roots. We would like to find out all roots of this polynomial given by the determinant equation. You can do it directly, but it will be complicated. We would like to make it much more easier. You can make this position or this position 0 and open up with respect to this column, or you can also make this position 0, and open it up with respect to that row. Or we have many alternatives. But what I've done, actually, I've done this position, make this position 0, make this position 0, by using the column operations. So I add this minus of this column to there, minus of this column here. Both of these operations, column operations, will not affect the determinant. So the determinant of this matrix will be determinant of this matrix. A determinant will not be affected by this column operations. And so what we have here in that moment is extreme x cubed minus 1, x minus 1, from here 7, 1. Opening up with respect to the last row, we have 0, 0, so I don't need to think about that this entry, it will give me 0. Only thing, this entry is non-zero. So this is the first row, third row, third column. So I have minus 1, third row, third column. And the entry here is 1. And the minor, by removing the third row, third column, will be the determinant of this matrix here, which is that one. So this will be plus 1, this will be plus 1, and the determinant of this will be this times this minus this times this. So I have a polynomial x cubed minus 1 minus 7 x minus 1. Just tidying up, this is x cubed minus 1. I can write it down as x squared, this one here, x minus 1, x squared plus x plus 1. So in both sides, it has x minus 1 is common. I'm taking it out. So I have x minus 1 here. And this one, this polynomial, can be factorized as x plus 3, x minus 3. So I have the root with respect to this factor, which is 1. The root with respect to this polynomial will be x is equal to minus 3 and x is equal to 2. You can check it. This times this will give me minus 6. This plus 3x plus minus 2x will give me just x. So multiplication of this linear factors will give me this quadratic polynomial. The roots of this polynomial given by this determinant formula will be just minus 3, 1, 2. Okay, now I would like to solve the question 70. Here it is given that A and B are n by n matrices, are the symmetric matrices. They're invertible, which means that the inverses exist. If we assume that the inverses exist, and we would like to prove that this equation is just an identity, it's just one. Now, before I start, I would like to remind ourselves what was the formulas, what we need to know about the determinant. So we can, if we have a determinant of A times B, will be the determinant of A times the determinant of B. This is a very important term, very important fact. And if A is an inverse, then we have A inverse, by the definitions of an inverse of a matrix. A inverse is equal to A inverse A is equal to identity matrix. This is a matrix form. If you take the determinant in every, in this equation, so this will be determinant A inverse, But because of the multiplication can be factorized in the determinant case, so I can rewrite them as determinant A inverse, that will be 1. So determinant A inverse, here it appeared, I can take this determinant of A on the right-hand side. So determinant of A inverse is really 1 over determinant of A. So basically, I can take the inverse outside to the determinant, because this is just as a rational number, this is 1 over 2, that is a 2 inverse. So think of that way, right? This is a real number, and this is the inverse of the real number. Here is the matrix inverse. The determinant of the matrix inverse is equal to the inverse of the determinant of the matrix A. So this is another formula that we are going to use for this question. Also, we know that the transformation will not change the determinant. So the determinant of a transpose of the matrix is exactly the determinant of the matrix. Okay, I'm going to use these 3 equations and make this expression simpler and try to find out it is equal to 1. So we have a transpose and a power. And then we have another matrix. I think the first thing that I've done here is just the multiplications of the matrices. I can rewrite them as the determinant of them. So I'm dividing all of those with respect to itself. So the determinant of A transpose will not change anything. So that will be exactly the A. So this is the 7th power here. Will stay there. I have B inverse. But when we apply the determinant here, everything in that moment will be just a real number, and I can change them, right? So this equation, all these factors can be interchanged each other because they are just real numbers, and real numbers are commutative. So I'm getting basically the determinant A and the power in one corner and determinant B in another place. So A transpose and A are exactly the same. So I have a power 7 here. I have a power 29 here. And I have a power of 36 here. So 7 plus 29 minus 36, which will be just 1, just 0, right? 36 plus 36 here minus 36 here is 0. That will be 1. And that will be 0. So any real number power 0 is just 1. So this whole thing is 1. And similarly here, determinant B inverse, I can do it in another way. So I will take that inverse outside the bracket of the determinant. So this is determinant of B inverse 15 will be determinant B of minus 15. This is what it is here. I have a determinant B11, so I have an 11 as a power here, and I have another power here, 4. So this will be minus 11 plus 11. Again, this number is 0. Determinant B of power 0. Determinant B is a real number. Power 0 is 1, so it is just 1. So yeah, it's a bit of a tricky question, this one. But it is important to know these facts. And the trick of this question was to determinant and the determinant of the inverse is the inverse of the determinant. So this fact was to finding out this one, observing or getting this information and applying to this question was a tricky part of this question, I suppose. That's about it. Thank you very much for listening. See you next time.